Titanium. It's the stuff of spacecraft, fighter jets, and life-saving medical implants. It's a metal so strong, lightweight, and corrosion-resistant that we named it after the Titans of Greek mythology. But for decades, this Titan has had an Achilles heel. Its staggering cost and the wasteful way we're forced to shape it. Traditional manufacturing, like carving a part from a solid block, can waste up to 90% of this incredibly expensive material. For some aerospace parts, you might buy 25 kilograms of titanium just to get a final 1 kilogram component. This has kept titanium locked away, reserved only for the most critical, cost-as-no-object applications. But that era is ending. A revolution is happening right now, driven by 3D printing, that is poised to make titanium not only dramatically cheaper, but also significantly stronger. This isn't just a small step forward. It's a paradigm shift that could unleash the full potential of this miracle metal across countless new industries. Welcome to G Fun Facts Online, where today we're exploring how 3D printing is forging a new age for titanium. For decades, the undisputed king of high-performance titanium has been an alloy called titanium 6-4, made of titanium, with 6% aluminum and 4% vanadium. It's a marvel of material science, offering a superb balance of properties. But it has two massive problems. The first, as we mentioned, is cost. The ultrafine, pure titanium powder needed for 3D printers can cost anywhere from $300 to $600 per kilogram. The printers themselves are million-dollar industrial machines. The whole process is so expensive that a printed 10-centimeter cube of titanium could cost you up to $50,000. The second problem is more fundamental, hiding at the microscopic level. When you 3D print with traditional titanium 6-4, the rapid melting and cooling creates a flawed internal structure. Imagine the metal is made of tiny crystals or grains. Ideally, you want these grains to be small, uniform, and packed together, making the part equally strong in all directions. But the 3D printing process forces these grains to grow into long, thin columns, all pointing in the same direction. This creates a hidden weakness. The part might be strong along the length of these columns, but dangerously brittle and prone to cracking across them. This unpredictability is a deal breaker for a jet engine turbine blade or a spinal implant. For years, we've been trying to fit a square peg in a round hole, using an alloy designed for old-school forging in a brand-new printing process. But now, we're finally starting to design the right peg for the right hole. The revolution begins with the printers themselves. Additive manufacturing, or 3D printing, builds parts from the ground up, layer by layer from a digital file. This minimizes waste and allows for impossibly complex designs. For titanium, three main technologies lead the charge. The most common is laser powder bed fusion, or LPBF. Inside a sealed chamber filled with inert gas, a machine spreads a paper-thin layer of titanium powder. A high-power laser then zips across the surface, precisely melting and fusing the powder to create one solid layer of the object. The platform then lowers, a new layer of powder is spread, and the process repeats thousands of times until the part is complete. This method gives the best detail and surface finish. Next is electron beam melting, or EBM. This process works in a high vacuum, which is perfect for a reactive metal like titanium. Instead of a laser, it uses a powerful electron beam. Crucially, before melting, the beam preheats the entire powder bed. This simple step dramatically reduces the temperature difference between the hot and cold zones, minimizing internal stress and creating stronger parts with less need for post-processing. It's faster than lasers, making it ideal for medical implants and aerospace parts. Finally, there's directed energy deposition, or DED. This is a completely different approach. Instead of a powder bed, a robotic nozzle sprays metal powder or feeds a wire directly into a melt pool created by a laser. It's like a high-tech, precision welding process that builds parts in open space. DID is incredibly fast and can create very large components or even repair existing high-value parts, adding new features to them on the fly. These technologies set the stage, but the true breakthrough, the alchemist's dream, is happening at the atomic level. The real revolution isn't just in the printers, but in the material itself. Scientists have finally cracked the code to solve titanium's grain structure problem. A research team from RMIT University in Australia pioneered a new way to design titanium alloys based on a principle called constitutional supercooling. It sounds complex, but the idea is brilliant. By carefully adding specific elements to the titanium mix, they can trick the metal as it solidifies. They create a condition where the liquid metal just ahead of the solidifying part is actually cooler than its own freezing point. This unstable state triggers the formation of new, perfectly uniform grains, disrupting the growth of those long, weak, columnar grains we talked about earlier. And here's the most exciting part. They discovered they could achieve this effect by replacing the expensive and rare element vanadium with something far more common and affordable: copper and iron. This two-part innovation, a new design method using cheap, abundant elements, has created a new class of titanium alloys. These alloys are reported to be up to 30% cheaper to produce than the old standard. And because they naturally form a superior internal grain structure during printing, they are stronger and more ductile, meaning they can bend more without breaking. We're now designing titanium not just for its final properties, but for the very act of being 3D printed. This innovation is already having a massive real-world impact. In aerospace, where every gram saved means less fuel burned, this is a game changer. The most famous example is the fuel nozzle for the GE LEAP jet engine. The original nozzle was an assembly of about 20 individual pieces that had to be carefully welded together. Using 3D printing, GE consolidated all 20 parts into a single monolithic component. The new 3D printed nozzle is 25% lighter and 5 times more durable. With over 30,000 of these nozzles produced, it's a proven success that powers modern aircraft like the Airbus A320neo and Boeing 737 MAX. In the medical field, 3D printed titanium is leading to a new generation of personalized implants. One major problem with traditional solid metal implants is something called stress shielding. Bone is a living, porous structure that needs stress to stay healthy. A solid, overly stiff implant carries too much of the load, shielding the surrounding bone, which can then weaken and lead to implant failure. 3D printing allows doctors to create implants with a complex, porous lattice structure that perfectly mimics the patient's own bone. This porous design reduces stress shielding and, more importantly, creates a scaffold for osseointegration, where the patient's own bone cells actually grow into and through the implant, locking it in place for a stronger, more permanent biological fix. And in the high-stakes world of motorsports, 3D printed titanium provides a critical competitive edge. In Formula One, where performance is a direct function of weight, teams use it to create incredibly lightweight suspension and gearbox components. Using software to optimize the design for strength and weight, they create organic, skeletal-looking parts that can only be made with 3D printing. One racing team created titanium suspension parts that were over 60% lighter than their machined predecessors, a massive advantage on the track. Despite these successes, the path to widespread adoption isn't without its challenges. The total cost of printing is still high, though innovations in powder production and faster multi-laser machines are driving prices down. Printed parts also aren't ready to go right out of the machine. They often need critical post-processing steps, like heat treatments, to relieve stress, and a process called hot isostatic pressing, or HIP, which uses immense heat and pressure to squeeze out any tiny internal pores, making the part almost perfectly dense and incredibly fatigue-resistant. But the biggest hurdle is regulation. For safety-critical industries like aerospace and medicine, you can't just print a part and install it. A long, rigorous certification process is needed to prove the part is safe and reliable. Organizations like ASTM International are creating standards, and regulatory bodies like the FAA and FDA have complex qualification pathways. Gaining their approval is essential for building trust and ensuring safety. So, what does the future hold? We are standing on the edge of a new era. The RMIT breakthrough is just the beginning. Scientists are now using AI and machine learning to rapidly design and test a whole new generation of designer alloys, created specifically for additive manufacturing. Soon, we'll see the rise of the digital twin, a virtual replica of every part being printed, updated in real time with sensor data. This will allow the printing system to make corrections on the fly, ensuring perfect quality and creating parts that are born fully qualified. As costs continue to fall, high-performance titanium will break free from its exclusive domains. We'll see it in professional sports equipment, luxury cars, marine applications, and even advanced energy systems. The story of 3D-printed titanium is about shattering old limits. It's about transforming a difficult, expensive material into one that is accessible, versatile, and fundamentally better. We are forging a future where the high-performance components that power our world and heal our bodies are not only superior, but available to all. The age of democratized titanium is dawning, built one layer at a time,